Derive an equation for the kinetic energy and potential energy for a simple harmonic oscillator and show that the total energy of a particle in a simple harmonic oscillator is constant at any point on its path. So first of all, what is a simple harmonic oscillator? Now basically this is a system in which you got any particle or a mass that actually undergoes an oscillatory motion and obeys the Hooke's law, which will be written as force is equal to negative Ke. Now this force is actually going to be the restoring force. That would always be the force that tends to bring the harmonic oscillator back to the equilibrium position. Now the negative sign here shows that the direction of the mass or the particle within that simple harmonic oscillator, it would always be returned to the equilibrium position. So let us say that you have this as that type of system, which is a simple harmonic oscillator. Now you could have the oscillation of this ball in this direction, could also have it in this direction. And so basically as it goes in this path and also returns, there is a greater force that tends to bring it back to this position, which this is the equilibrium position. So there is always going to be a force that will tend to bring the ball or the mass or the particle back to this equilibrium position, and that force will be given as a negative Ke. So you just need to know that. Now next up, we know that force, that is equal to mass multiplied by acceleration. Now what do we know the velocity to be? Velocity, that is the same thing as a change in distance or displacement with respect to time. Now, if I wanted to find dv dt, that will be the acceleration. Now, we already know that v itself is this, isn't it? So this is going to be d dt, and that will be with respect to dx dt. So this will be d squared x dt squared, and that is equal to a. That means acceleration is equal to d squared x dt squared. And so that will be equal to a. Therefore, we can write the force in this way. This will be, so I need to rewrite that. That will be d squared x dt squared. This is the same thing as the acceleration for the body. So because we have force to be equal to negative Ke, and force is going to be equal to ma, or m equal to this, we're therefore going to have something like this. This will be mass multiplied by d squared x dt squared. This will be equal to negative Ke. Now I'm going to take this to this other side. That is by means of dividing through. So that will be d squared x left. So this will be dt squared. This is going to be equal to negative K divided by m multiplied by e. Now let us try to make e, which is the extension, let us call it as x. That is the distance which the oscillator moved away from the equilibrium position. So instead of writing the e, I'm just going to represent it or replace it with an x. So in that case, we're going to have a d squared x dt squared. And so this will be minus k divided by m multiplied by x. Now I can easily take this stuff and make it to all be on the left hand side, and I'm going to have a 0 on the right hand side. So that will be d squared x divided by dt squared. So this will be plus k divided by mx. This is going to be equal to 0. Now, if you wanted to integrate this stuff, The integral part of this stuff is going to be the solution to this equation. Now you need to know that this is a differential equation. So if I want to find the solution to this differential equation, I need to integrate it. Now by integration, I'm going to have x that will be equal to a cos omega t plus phi. This is going to be the equation that will be formed. Now we know that omega is equal to 2 pi f in it. Now we also know that f is the same thing as 1 over 2 pi. That is 1 over 2 pi. And that will be multiplied by k divided by m. So if I took this and multiplied it with that stuff, that will be omega is equal to 2 pi multiplied by 1 divided by 2 pi. This will be multiplied by k divided by m. Now this is going to cancel this out. So I'm also going to have omega to be equal to square root of k divided by m. So that is one thing you really need to hold at the back. Now if I wanted to have omega squared, that is going to be this stuff all squared. That should give you a k divided by m. So you need to hold these ones. They're really going to be very useful. So I'm going to wipe these ones out now. Now from here, we're going to do very many things. First off, we're going to try to find out what is kinetic friction. Well, that should rather be kinetic energy. Kinetic energy is going to be equal to half mv squared. Now what is v? We know that v should be equal to dx dt. That is the derivative of x with respect to t. So if we had x to be this stuff, we could find dx dt, which is a v. So v is equal to dx dt. That means I need to differentiate this with respect to t. So if I want to differentiate this, first I need to rewrite everything that is there. So this will be well, before I do that, I need to write a first. Now this stuff needs to be differentiated. Now the derivative of cosine is a minus sign. So that will be minus sine omega t plus a phi. Now this phi is a constant. That is a phase angle. If you add it to this, basically these are the phase angles. Now we need to differentiate the angle also. This is going to be a constant, so the derivative of that one is basically going to be 0. So we need to find the derivative of omega t. With respect to t, that is going to be omega. So that will be what we'll be left with. So that is what you got. So let us rewrite it. Now rewriting it, we're going to have that v. V is going to be equal to minus a omega. So this is going to be sine. This is going to be omega t. And this will be plus phi. So that is what you're going to have. Now what if we wanted to square this? What is that going to give us? Now if we squared that, v squared, that is going to be negative all squared, which is going to be a positive. And a all squared is going to be a squared. This is going to be omega squared. And this stuff is going to be sine squared omega t plus a phi. So therefore, the kinetic energy is going to be written as 1 over 2 mass multiplied by this stuff, which this is going to be a squared omega squared, and that will be sine squared omega t plus a phi. So we know that omega, that is equal to square root of a k divided by m. Now we already know that omega squared is going to be K divided by M. So I can rewrite this. So if I did that, what am I going to have? So I'm going to take these ones out. So let us say that I used omega squared as a K divided by M. So the kinetic energy will be 1 over 2 multiplied by mass multiplied by A squared. That will be multiplied by K divided by M. This will be multiplied by sine squared theta of, well, that is sine squared omega t plus a phi. So this is what you have. Now this is obviously going to have this M cancel. So the true form of the kinetic energy, that should be equal to 1 over 2. So here we're going to have a squared. I think I'm going to place these ones in brackets. So this will be a squared. And here we're going to have a k, and this is going to be more. I think I'm going to start with k. So this is k multiplied by a squared. And here we're going to have a sine squared omega t plus a phi. So this is the real form of the kinetic energy. So that is basically it. Now next up, we need to find the potential energy. We know that this is a simple harmonic oscillator, and so because of that, we know that the potential energy, so I need to rewrite that. The potential energy for that should be equal to 1 over 2 kx squared. That is what I'm going to have. So I'm going to take these ones out. Hopefully by now you remember them, so I don't really need to write them there now no more. Now, the only thing I need to do is to square x. So I need to square this. Now if I square this, this is going to be x squared equal to a squared. And here we're going to have a cosine squared omega t plus phi. So this is what I'm going to have for that one. So the potential energy, that is going to be equal to 1 over 2. So this will be 1 over 2 multiplied by k. That will be multiplied by a squared cos. So that is cosine squared omega t plus a phi. So this is what I'm going to have for the second one. That is the potential energy for the simple harmonic oscillator. Because this stuff performs simple harmonic motion, that is going to move in this form. And basically this is going to be the energy of objects and the potential energy for objects which are actually performing simple harmonic motion. So I need to take this one out now. This is also going away. So this is going to be the formula for the kinetic energy. This will be the formula for the potential energy. Now we also need to show that the total energy of the particle in a simple harmonic oscillator is constant at every point. Now if that is going to be constant, that means there is no time for it. So first of all, we know that the total energy of a system is always going to be the sum of the kinetic energy added to the potential energy. So we need to add the two of them. So first, we need to have this added to this. So I'm basically just going to write it there. So that will be 1 over 2 k multiplied by a squared. This will be sine squared omega t plus a phi. I think I need to rewrite this. So that is what you got. Now we need to add it to 1 over 2 Ka squared. This is multiplied by cos squared omega t plus phi. So this is what we got. Now from here we know that a half is common for both terms of the kinetic energy as well as the potential energy. You could also factor K out as well as A squared. So we're basically going to take all of them out. So that will be 1 over 2 Ka squared. That will be multiplied by sine squared omega t plus phi. And that will be plus cos squared theta. Well, that should be cos squared omega t rather, plus phi. So this is what I'm going to have. Now we already know from the trigonometric identities that if you got sine squared of an angle, let us say omega t plus phi in this case, and I added it to cos squared omega t plus phi, this is going to be equal to 1 because the sine squared of an angle added to the cosine squared of the angle, that should give us a 1. So whatever the angle is basically doesn't really matter. So we're not really going to focus on what is inside of the angle. We just know this angle is the same thing as this. So far as that criterion is fulfilled, and this is always going to be equal to 1. So because of that, this whole stuff reduces to a 1. So the total energy is going to be equal to 1 over 2 K multiplied by A squared. And so this is basically what you're going to have. So as you can see, there is no time parameter which is included within this equation. Because of that, we can say that this is constant because there is no time. And so because of that, it is constant. So basically that will be the answer to the question.